Now, as a second topic, let's consider shearing stress in thin-walled member. So, for thin-walled member, as I told you, this is the case when we have the thickness much smaller than the height of the beam, so that you can think about really thin cross sections. Okay, so for this case, what you can imagine is following. So when you have a cross section like this, and if you think about like a little tiny section out of this, okay, yeah, let's take this as our section of interest. So what you can imagine here is, let's see, yeah, this is your original shape. So, and this is this colored region is our cross section. Suppose that you have free surface here, so the tau must be 0 here, and tau, the other free surface, is 0. So you can have only non-zero tau here. So, and imagine that if you have a shear stress component like here, and if you want to have shear stress component here to satisfy mechanical equilibrium between this stress and that stress, you need to have a stress in this free surface too. Okay, so the only way you have to satisfy tau equals 0 at this side and tau equals 0 in this side is that your stress must be parallel to this thin-walled member. Okay, so only if you have this stress flowing parallel to your thin wall, then you can satisfy tau equals 0 condition for your thin-walled member. Okay, so having recognized that, you can obtain the distribution of shear stress relatively easily, and the direction of shear stress can be any direction that is parallel to the thin-walled member direction. Okay, suppose that you have this hollow cross section with the thin walls. Then if somebody asks you to draw shearing stress at this position regarding the direction, you can easily say that the direction must be parallel to this thin wall. And regarding the magnitude, what you can realize is out of this red area, you can obtain the Q integral. Okay, and after obtaining Q integral, and you can also recognize that you have like exactly same shearing stress here and there, because due to the symmetry, then you have a 1/2 factor, and you have VQ over IT, our equation, and the integral range of Q is this curved area. Then you can obtain shearing stress. Okay, so when somebody asks you the question regarding thin-walled member, you don't need to worry about the direction. Direction must be parallel to the direction of a thin wall. And regarding the magnitude, you can take the effective and very nice red area, such that you can perform Q integral and obtain the shearing stress by applying this equation. Then you can determine it. Okay, so let me give you some example. Suppose that if somebody asks you to obtain the shearing stress distribution when there is shearing force V, and actually the answer goes as follows. And how if somebody asks you how we can obtain the distribution, the answer I want to tell you is we have to have some sort of rule of thumb. Okay, so the first idea I want to deliver is try to take the area with very high portion of tau equals 0 or free surface. Okay, so if you think about my first rule of thumb, it's following. So if you want to obtain the shearing stress at this point, what you do is you take your red area in this way, such that at the top, at the bottom, at the side, you have free surface and tau equals 0, tau equals 0, and tau equals 0, and the direction is here. Okay, so if you consider your Q at area 4, it must be delta H over delta X, and you can apply V over I Q, the red area integral, and Q red area integral is the centroid position multiplied by area, which is L times T. The L is distance from the end of the flange. Okay, so you can obtain tau by dividing q by thickness t, and the answer must be v over I y bar, the centroid position of this guy, which is y bar, right, and multiplied by L. L is the distance from the end. Okay, so this is how you approach this problem. Okay, now if somebody asks you to draw and obtain the magnitude here regarding the direction, you know that direction must be downward, but regarding the magnitude, if you take this red block, it's it's not easy to apply this method because you have first unknown. Suppose that even though they are symmetric, there is one unknown for tau here, and there is another unknown. Because you have two unknowns and you have one equation, you cannot solve for q out of our equation. So here the solution to this problem is you take the entire full flange as a red area and try to take this as your red area. Then try to apply our equation, and the q integral range must be the entire range. And here what you can see here is 1, 2, 3, 4, 5. All these areas you have free surface or tau equals 0, and you can obtain tau as a function of VQIT. Okay, now out of these discussions, what you can realize is following. So when you draw the shearing stress distribution, and if you think about the distribution of Q, it goes as follows. If you have this thin-walled member, and suppose that they are connected in one point, and suppose that you have a longitudinal stress here, longitudinal stress here, and vertical stress here, they have a some relationship. The special relationship is Q3 must be same as Q1 plus Q2 when you have this connecting node. Okay, the reason is following. So when you obtain Q1 or Q2, you obtain either this blue one, either that blue one to obtain Q1 and Q2, and perform this Q blue area integral. Now, if you obtain the Q3, then the integral range of this Q integral is entire flange area. Then, if you compare this integral and that integral, this integral is twice of this blue integral, right? And the other terms v and I are equal to each other between Q1 and 2 and Q3. Okay, that's why you have to have Q3 equals to be Q1 plus Q2. Of course, we can think about asymmetric thin-walled beam, something like this, and it will satisfy Q1 Q2 Q1 plus Q2 equals to be Q3 if there is no twist. Okay, regarding the issue of twist for this non-symmetric cross beam, we're gonna discuss that in next video. But even for this non-symmetric cross section, and if there is no twist, we can very easily show that Q1 plus Q2 must be same as Q3. Okay, so with this, let me close my discussion on thin-walled member. And regarding the thin-walled member, the only thing you have to remember is this fact. The shearing stress must be parallel to the thin wall. Other than that, it's the the matter of the defining the red area effectively and obtaining the Q out of Q integral. Okay, so let me close the lecture here.